All right, so we're glad to have Prateek Agrawal visiting us from Santa Barbara, where he recently moved, and he'll tell us about supercooling and confinement. Go ahead.
Thank you for the invitation. I'm very happy to visit. It's my first time visiting UCSB. I thought it'd be fun to talk about some recent work that I've been doing with people back at Oxford. So Gaurang is a graduate student, advised by John March Russell. And Varja and Mario are postdocs. But Varja is moving on to University of Maryland. Mario is now at CERN, all excellent young people. And so I think the story is interesting for the following reason, that it sort of takes a phenomenological application of a formal question that we're interested in, and there's a good dialogue between the two there. The question of confinement is a formal question we've been interested in for a long time. And it turns out we're also interested in it for phenomenological reasons, as I will show. And actually, the specific aspects of it that have implications for phenomenology actually maybe shed light on the basic problem of confinement itself. So we might learn something new about confinement itself by pulling on a thread, which we wouldn't know to pull unless we were looking for that phenomenological application. Okay, so I think that's pretty cool. So here, before I get into the details here, the key takeaway, the confinement is, of course, a fundamental open question. We would like to understand it in as many contexts as possible. And here, we're going to look at the properties of confinement, a confinement phase transition, a thermal confinement phase transition, as motivated by potential gravitational wave signatures it can produce. And it will point us to this specific feature in confinement phase transitions is the issue of supercooling, whether these confinement transitions are supercooled and to what degree are they supercooled or not. And this is something that is something which is not maybe a natural question if we're asking about questions, say, on the lattice or formal questions, which are usually at the critical temperature or at equilibrium. But this sort of dynamical question of supercooling turns out to be very crucial for understanding the gravitational wave signatures. And also turns out to be something maybe we can actually learn something about on the lattice. So this is a very widely studied topic. One of the benchmarks for LISA, the space-based gravitational wave observatories, are cosmological phase transitions, and confinement phase transitions, broadly speaking, are one of the targets for that. So it's one of the big physics cases for new physics cases for gravitational waves in the near future. And typically, there's an entire field working on it, and most of that field considers something like a Randall-Sundrum model, which has been studied in this context that produces supercooling. And in these models, people have shown that there is substantial supercooling, which we'll see is one of the prerequisites for producing detectable gravitational waves. But we don't actually know exactly what the dual quantum field theory to a Randall-Sundrum model is. What strongly coupled field theory are we studying when you're talking about RS model? And this is a generic feature. We would want to ask whether a confining transition would have strong supercooling. And this chain of thought actually will lead us to make an estimate or a prediction. Prediction is maybe too strong a word, but for saying that, for example, in something like SUN Yang-Mills theory, the confining transition is not supercooled. By not supercooled, I mean that the maximum supercooling is of a few percent. In other words, if you go to the critical temperature, you're in the deconfined phase, you go a few percent below critical temperature, there's just an instability and you go into the confined phase. There's not a strong supercooling where you go order 1 below the critical temperature and you stay in this metastable deconfined phase and then the transition. Okay, so that I will present various sort of tangential evidence, pieces of evidence for that, and this is something which we're trying to encourage our lattice colleagues to actually test, which might not be completely impossible. Okay, I should say, if there's any questions at any time, you should just feel free to stop and ask. There might be people might be aware of different aspects of these things at different levels. So just please ask any background questions that if I'm going too fast or any stuff. Okay, so just to set as a motivation, I'm not going to talk too much about the details of the gravitational wave generation themselves, but just to set up a motivation, here is what typical plot for gravitational waves from an early universe phase transition might look like. So here, this frequency of the gravitational wave, the LISA sensitivity peaks at around a millihertz, and this is a canonical sort of power in the gravitational waves as normalized to the critical density of the universe. That's plotted. And so here you see that LISA has a certain sensitivity to some stochastic gravitational wave signature, the gravitational wave signals that were generated in the early universe. And here I've drawn a cartoon of what a first order phase transition in the early universe might produce. And you have chosen parameters, so as this is actually within LISA sensitivity, but these are reasonable parameters one might hope a phase transition might have. What features are important for this phase transition is that the phase transition should be first order and should have strong supercooling. Trying to see how much of the region. So there's various features of the phase transition that this signal depends on. For example, here's a formula that I've taken from this review, which is essentially parameterizing numerical simulations of phase transitions. And so this does not follow some analytical calculation. You have to actually just run a numerical simulation, see how the phase transition progresses, and extract from it what gravitational wave spectrum you would get. And there's a couple of key dependencies that you want to focus on. One is this VW, which is the wall velocity, which is just if the phase transition is happening, if the first order phase transition is happening to bubble nucleation, the bubbles are formed. And if they were just expanding in vacuum, they would just accelerate very quickly to the speed of light, and then they would collide at speed of light. But typically, they're expanding in a plasma. There can be friction, as the bubble wall velocity can actually be substantially smaller in some cases. So that has some dependent. The gravitational waves depend on that. The other key parameter the gravitational wave depend on is this parameter called beta, which is essentially the time scale for the phase transition to happen. And this ratio beta over H star is anywhere from a few 10 to 100 or larger. And just for going rates, 10 to 100 is something you might be able to see. Beta much larger than that is undetectable. Beta much smaller than that means your phase transition is so suppressed that probably you end up in a phase of eternal inflation and the phase transition never completes. Okay. Roughly speaking, the frequency of the gravitational waves is set by the size of the Hubble horizon at the epoch of generation. So when the phase transition is happening, the typical causal length is given by the Hubble scale at that point, and then the gravitational waves are generated with that frequency, and then they decouple from the rest of the universe. They redshift like radiation, so we can just track back a given frequency, say a millihertz, would have to be generated at the weak scale. Okay, so that's the motivation for thinking about this particular channel, where we think there's maybe new physics at the weak scale. We know the standard model phase transitions themselves, by the way, are all too weak. They're not first order. They're crossovers to actually produce gravitational waves. Both the QCD phase transition as well as the electroweak phase transition cannot, in the standard model, produce gravitational waves at an appreciable level. But around the TeV scale, we might imagine if there's new physics associated with the Higgs sector, or there's new strongly coupled dynamics, they would have associated phase transitions, and they could well produce a first order phase transition. So we might actually learn about, say, 10 TeV physics first by its gravitational wave signature. Okay, so this favorable fact that around the weak scale, transition temperature actually happens to lie right in the frequency band of LISA, then forces us to ask the question, well, okay, so then if there's new physics at weak scale, what features must a phase transition have to give a loud signal? Okay, and it should be a first order phase transition. And the other parameter I was saying was supercooling, which is correlated with this parameter beta. So here's an empirical demonstration of that fact. In this expression, there's no explicit dependence on epsilon on the strength of the phase transition. This is the way we choose to empirically represent what the simulations actually are showing us how much gravitational waves are produced. But epsilon, which is just defined as this, the temperature at the amount of supercooling. So if at a given temperature, it's just the ratio of the temperature to Tc. Supercooling is very strongly correlated with the amount of with beta itself, the time scale of the phase transition. So this is showing the correlation between epsilon n, which is the supercooling at the epoch of nucleation, where somehow some defined fraction of the universe is in the new phase over the old phase, versus what beta that particular simulation has, and then you can see that there's a very strong correlation between them. And indeed, if you have supercooling less than 20% or something, numerically already it looks like the beta is going to be too high to actually be very, very important. Ultimately, this is sorry.
I'm just not understanding your definition of supercooling.
So
TC is the critical temperature.
TC is the critical temperature of the transition, and epsilon, let's say, is another temperature variable. So at any given T, you said what is the supercooling so far? It's 1 minus T over Tc. Then you can ask at the nucleation what is the amount of supercooling, and that's this thing. So there's a nucleation temperature, then that T would be Tn. So epsilon is for epsilon. Supercooling is just saying it's like a temperature variable saying how far down the supercooling barrel are we. And supercool, how much a given transition is supercooled, you might want to parameterize by epsilon n, whereas at the nucleation temp, what was the nucleation temperature relative to the critical temperature? But nucleation temperature is defined as some complicated thing of calculating. There's bubbles of all different sizes, so you integrate over the entire volume and calculate the fraction of the universe that is in the confined phase versus the deconfined phase. And that gives you the temperature at which it's 77% or whatever the percolation limit is or whatever.
Before your phase transition.
No, so hit the phase transition means TC, you mean? Yeah, so this is all below us. So you hit TC, nothing happens because at TC the tunneling action is infinite. And below TC you start populating bubbles. And at certain temperature, you have enough bubbles populated and enough which have grown and new bubbles are popping in. So enough fraction of the universe is in the confined phase so that now this phase transition will percolate and complete. So there's that epoch which is defined as the nucleation or percolation epoch. Not exactly the same thing, but there's an epoch you define which is below TC, where you say the phase transition has quote unquote completed. And again, this is all parameterization of simulations where you actually then say, given that number in a given phase transition, I can map it to this strength of gravitational wave. So this beta GW, for example, is some number that is you calculate in a toy version of that in your model, and the simulations have some version of that, and you match that. Does that answer your question? Yeah. Right. But in fact, it's not just sort of this numerical fact about beta being large that is the problem. If the supercooling is small, then it can actually be much more. It can have much more dramatic effects. So if your supercooling is really small, as in a few percent, then as you have a bubble nucleation, that nucleation event releases a large amount of latent heat, and so it reheats the universe up a little bit. And if your supercooling is really small, then reheating it just by a little bit brings you back up to critical temperature. And so suddenly the pressure on the outside and the inside are equal. That's the definition of critical temperature. And so the bubbles don't actually expand out. So when transitions are very supercooled, you don't get this sort of thing, this picture of bubbles popping out, expanding, becoming speed of light, and colliding violently. You actually get the bubble popping out. You get back at the critical temperature. You cool down a little bit because the universe is still expanding. And so you just sort of slowly expand out instead of violently colliding. And that completely kills anti-gravitational waves. It's not just a numerical suppression, it's completely fatal to gravitational waves. So for small supercooling, we can sort of, this is actually, by the way, this is a qualitative picture. And people have estimated what the wall velocity would be in that case, but they did some sort of order hand-wavy estimates of the transport coefficients in the plasma and so on to see how that latent heat that's generated by the bubble popping out is transmitted into the rest of the universe. But sort of qualitatively, it's going to be orders and orders of magnitude suppressed. And actually, an interesting question to figure out exactly what that phase transition looks like, which hasn't been done in very rigorous detail. So small supercooling, as we're arguing, is happening for SUN phase transitions. Is actually going to not just be a quantitative thing, but a qualitatively different phase transition altogether. So for the most generic case, what we would like to understand is this confinement transition happening in some non-supersymmetric theory, which is obviously a difficult question. And so traditionally, it's been approached, confinement itself or strongly coupled gauge theory has been approached through various indirect handles, usually involving supersymmetry and ortholography. And even for confinement, we get sort of inspiration from these examples, which are, for example, let's say we want to study SUN. One of the things to understand is just SUN Yang-Mills confining transition. That is maybe too hard, but we have supersymmetric examples, we have holographic examples, which are not exactly SUN. There's some sort of Yang-Mills adjacent theories or with more structure, which actually shed light on what this problem could be. And so when we talk about actually thinking about confining transitions for an application such as the gravitational waves, usually people are thinking about some kind of analogy or holographic dual model that people write. So the poster child for what these transitions, what a strongly coupled gauge theory transition in the early universe would look like in phenomenology is usually channeled through the random syndrome model. And so the random syndrome model is, if you haven't ever heard of a random syndrome model, I doubt you'll learn it here, but feel free to ask questions about it. It's a slice of ADS space bounded by two branes called an IR brane and a UV brane. And this is, roughly speaking, holographically dual to a strongly coupled gauge theory, where the UV brane plays the role of coupling the strongly coupled gauge theory, strongly coupled gauge theory, which is an approximate CFT, and the UV brane plays the role of coupling that CFT to gravity, and the IR brane plays the role of spontaneously breaking the CFT. So this is this is a geometric model in 5 dimensions. It's supposed to be dual to a 4-dimensionally strongly coupled theory, as for example, may complete the standard model. So the standard model might be completed by composite Higgs and some strongly coupled theory above, say, a few TeV scale. And coupled to gravity, if you want to couple it to gravity, that produces this effect that's captured by this UV brane. And at least in the first original tuned RS model, the role of the IR brane was to produce an IR scale akin to confinement, but it's also thought of as a spontaneous breaking of the conformity. So this feature of spontaneous confinement is something which is, from the 4D point of view, is somewhat bizarre. I don't think we know very many non-supersymmetric examples, at least of cases where there's a gauge theory that confines. It's a strongly coupled gauge theory that confines, but also that confinement is actually a spontaneous breaking of the conformal limits. Okay.
Does it come with an associated modular space?
Yeah. So in the tuned model, so it's bizarre. It's almost unknown. Examples are almost unknown in 4D. In 5D, it's also bizarre. Where does the bizarreness come in? What you have to do is you have to actually tune the tension of this brane to a very specific value with the bulk cosmological constant in order for this to be a stable geometry. And once you've done that tuning, there's a flat direction. You can place the brane anywhere. So that radion is actually that would be the exact masses because you did the tuning. So from the 4D point of view, it's really bizarre because we don't actually know how to construct examples, not supersymmetric examples with massless dilettants with spontaneous breaking easily. In the 5D case, it at least gives you a prescription. You do this tuning, and so the first RS model, which is not the one we studied, the first RS model is the one with that tuning and a massless radion. And of course, there's a tuning and then there's a massless radion. But that was very quickly resolved by Goldberg and Weiss by adding a small breaking of conformal invariance, so that actually this radion picks up a mass and this brane is stabilized. But you can use, typically people study, for calculability reasons and other reasons, people study the regime where this extra Goldberg-Weiss mechanism is small, has a small back reaction, and so the radion is typically light in these cases. And so you still have sort of this approximately spontaneously broken CFT in this case, which is very different from our experience with QCD, for example, of confinement, where confinement beta function is running at order 1, and so there's no approximate conformal invariance close to the IR. But in this case, the typical case of people study is that there's an approximate conformance. Okay, and that is indeed the sharp weird feature about RS, which is hard to replicate in gauge theory and seems crucially important for producing these first order phase transitions, which would be different from a generic confinement condition. And before we do the Goldberg-Weiss stabilization, there's no scale in the problem. It's really a conformal field theory. And if you turn on a temperature, the IR brane disappears behind a black brane horizon. And so at any temperature, this theory is just like a CFT would be, is in the deconfined phase. Okay. When you have Goldberg-Weiss stabilization, it generates some IR scale by dimensional transmutation. Most studies, when they use this RS picture, they assume small back reaction. And in the small back reaction regime, there's a light radion, and confinement is mostly spontaneous. And the tunneling action is very large for this transition. So the way the pictorial way the transition works is that at very high temperatures, the IR brane is behind a black hole horizon. Below the critical temperature, a bubble of the TeV brane appears from behind the black hole horizon, and eventually these bubbles coalesce and then form the IR brane, which is basically which is supposed to be dual to the confined range. Okay.
Sorry, what do those words mean? Confinement is mostly spontaneous. I understand there's a light radion, which is stabilizing the modulus, but what do those words mean? It's mostly spontaneous?
The lightness of the radion is because, so when you tune the brane tension, then there was really a spontaneous confinement, where you would say it's spontaneous confinement because the IR brane was associated with confinement, but also a spontaneous breaking of the conformal invariance. The radion was exactly massless. So if I break conformal invariance by a small amount, then you get a light radion, and the lightness of the radion comes from approximate conformals. So you still get a light radion, so you get a pseudo-Nambu-Goldstone boson. So it's still just like chiral symmetry spontaneously broken in the standard model. This is the same. This is but any real world strongly coupled gauge theory, you just say everything becomes order lambda QCD, and there's no sense in which you can talk about it as a spontaneous way. So in general, it's an interesting question, by the way. But there's a light scalar spin. There's a light spin zero CP-even particle here that couples like the Higgs to the standard model. And so there's an interesting question in general of what conditions are there that you can actually get a light radion in a non-supersymmetric theory. And this is a geometric construction, but it can be made natural, technically natural, what have you, in the geometric construction. But I don't know of a way to actually think about the 4D gauge, thinking about the 4D gauge theory dual and saying, under these conditions, the structure gives you a light radius. I don't know if it exists. In fact, the tunneling action is large. In fact, the first papers that pointed this out, they pointed out there's a problem in this theory because for this, so lambda here is some weak coupling, which is related to the fact that the back reactor is small. So it's actually lambda is actually usually small, but you can push a parameter space to lambda being order 1. But even then, you pay this n squared that you'd expect for any confinement deconfinement transition, and so you'd think that this action is too large. Just to give you some numbers, for around a weak scale transition to complete, n should be order 10. So the action should be order 100. And the whole RS, the reason that RS is calculable as a nice effective field theory is due to a large n expansion. And so the large expansion of RS is really valid for n parametrically bigger than 10, because there's about, let's say, 100 standard model degrees of freedom. So RS effective field theory, which requires n to be, say, parametrically bigger than 10, clashes against this tunneling action, which is actually order, which has to be less than 100 for phase transitions. So this was typically thought to be a problem in RS cosmology, that this phase transition actually is too supercool and never completes, and you get eternal inflation. So you maybe have to have reheating temperatures below the TeV and so on and so forth. So there was RS cosmology usually had this one problem that people thought was always lurking in the background. If this feature of having a very tunneling actions is large. And so the question we wanted to ask is this generic, and what Fourier theories does this correspond to? Maybe I should pause if there are any questions about so.
So standard Yang-Mills is not too supercool. Pure yet. Pure is
So we don't know explicitly, but I'll present as my final punchline evidence that it is not supercool. We don't know. And so the lower, I can tell you, the lower is, before we started, maybe not everybody agreed in the field, everybody thought that this is the field, but certainly the lower was that take large n SUN, the confinement deconfinement transition action should scale like n squared, just for general grounds. N is large. So this is a very large action tunneling transition. So you should just have supercooling. So large and gauge theory should have strong supercooling. If you have a large and gauge roughly SUN, but any other large and gauge theory confining in the early universe, you should see gravitational wave. That was the generic sort of lower statement. And for SU, I'm going to say that that's actually probably, I'm going to argue it's not true. It would be good to check.
And what specific feature of this, just as a small teaser, what specific feature of this, these models are not replicated in pure SUN, which is critical for this supercooler?
Yeah, so here the feature that the confinement is mostly spontaneous is crucial. There's a light radion, and in some sense, confinement is driven by. See if I'm going to talk about this. No. Let me say that now. So the way people calculated this is they consider the effective field theory of just the light radion, and so light radion has some potential, and you calculate the action for tunneling this grain as just the action required to tunnel the radion out from infinity down to whatever value it settles down at its value. So there is a gravitational part of this whole action that is usually ignored and maybe argued with subdominant, or at least it's not making, at least the action will only increase if you include the gravitational part. But you only take the effective radion part, the one scalar degree of freedom, the radian part of the tunneling action to estimate what the tunneling action will be. And so a light particle that is driving that confinement transition is crucial for this whole calculation to be able to be done. And I'll show you already very RS-like examples where you try to actually make this this sort of starts failing. Any other questions? Okay, so let's think of what we don't know is what is the dual gauge theory in the RS case. Let's try to ask what happens in the cases where we sort of know what the dual gauge theory is, at least qualitatively, and what the status of supercooling is in those things. So the classic example is ADS-CFT as it was first posited. The classic case is that you think about a transition in global ADS with a boundary which is not R3, but not spatially infinite R3, but S3. So the dual theory is if you took ADS 5 plus S5, whatever, then you'll get n equals 4 super Yang-Mills, and that n equals 4 super Yang-Mills in this case would live on an S3. So that S3 gives a explicit scale to the CFT. And so the thermal confinement, if there was no S3, if you just did it on R3, then there's no scale. The CFT again will always be in the deconfined phase. On S3, there's an intrinsic scale, so you can talk about a confining transition as the ratio of the thermal circle S1 radius and the radius of the S3 that you put the CFT. Okay, and in some sense, and so this was the first example, of course, of thinking about holography and confinement. This classic Witten paper in the 98, very close after the original ASCFT proposal. But also, already it was pointed out in this paper, while this has the same sort of, this seems holographically dual to a confining transition, there's various sort of qualitative features which is not really what we think of as confinement. First of all, you're putting the CFT on a closed manifold, so there's the global constraint of having gauge invariant only charge neutrality, and so just any operators that you write down unless are necessarily sort of color neutral. And so then once your S1 actually becomes the same size as S2, this constraint starts to matter, and you start just seeing only gauge invariant objects because the kinematic constraint of putting it on a closed manifold is actually important now. Typical excitations are of the order of the sphere itself. And also, technically, it's really only a phase transition at n equals infinity, because it's a finite volume system, so we can't really technically have a phase transition if there's finite n degrees of freedom. But in any case, qualitatively, this was thought to be one of the really cool things about holography, that it actually gives you at least a qualitative transition that looks similar to a confining transition. And it was understood that this is, in the 5D picture, it's a transition between ADS Schwarzschild geometry, which is dual to the confined phase, and a thermal ADS, which is dual to a confined phase. And so this transition between confinement and deconfinement was in some qualitative way dual to the Hawking phase transition. And so let's see what happens in this case. How would supercooling get? And so this is a cartoon of what the free energy of the two phases looks like. This is the temperature in some units, in some ADS units on the x-axis, and it's the free energy of various phases. So as we start from high temperature and look for classical geometries, we get two solutions, two black hole solutions. One is called the large black hole, and the other is called the small black hole. And the small black hole solution is classically unstable. The large black hole solution is stable, and that is the lowest free energy solution. So that dominates the partition function. In other words, the stable phase in this at high temperatures is this large black hole ADS Schwarzschild metric, which is the deconfined phase in the gauge in the language. And there's another possible classical solution, which is just thermal ADS, just the gas of gravitons or whatever you have, and that's this free energy. Like this plot is normalized to the difference from thermal ADS. At certain temperatures, the critical temperature for this transition, the thermal ADS free energy becomes smaller than the large black hole temperature, and so that will become the classically dominant phase. And that would be the critical temperature for this deconfined confinement. And shortly after that phase, actually, what turns out to happen is that the smaller black hole branch and the big black hole branch meet, and the black hole branch stops existing altogether as a classical solution. So in the case of the confinement transition, we have a story where you have the critical temperature, you supercool a little bit, and the metastable phase just stops existing as a classical, semi-classical phase itself. So the deconfined phase just doesn't exist anymore. And if the universe was stuck in this deconfined phase at this point, it's classically will roll off to the confined phase, resistance stability. And these two things happen to be actually close to each other. This is not completely novel. We found Chris Herzog actually has papers which points out I'll say in a second why. But these actually happen to be very close to each other. And they're parametrically close in the number of dimensions d. In this case, the supercooling goes like 1 over d squared. The maximal supercooling that this transition can have before there's an instability is 1 over d squared. And so Chris Herzog and Emperan and friends have been looking at 1 over d expansion and holography and thinking about theories. And they've noticed that actually these things merge in the life, in the limit values. But even just for a 4-dimensional CFT, the maximal supercooling you'd expect in this particular case is about a few percent. And so these expressions have been staring at us for a long time, but so this question of how much supercool it is not really a question anybody sort of really asked for whatever reason. And it's parametrically small indices. Okay. But there was features of the putting the theory on S3, which was sort of slightly different from what the RS model really, or even what we think of a 4D confining theory on infinite space would look like. And so we could ask questions about something like a Klebanov-Strassler construction. And I won't go into details, but again, ask me in an hour offline some more details of it. But Klebanov-Strassler is again a holographic construction closely related to the n equals 4 superangles example, but crucially, it's not n equals 4 superangles. There's actually a theory that actually runs and eventually confines. So there's a geometrical picture of the Klebanov-Strassler construction, but there's also a gauge theory description of it. And this is thought to be as close as you can get to the RS model itself, where there's actually a running coupling, there's actually a running gauge theory that eventually confines. And people have been studying numerical simulations of black holes and the black hole transition in Klebanov-Strassler geometry instead of, and it's not as you can't actually have analytical traction as in the ADCF, the pure ADCFT case. And numerical simulations again indicate there's an instability very close to the critical temperature. So again, the estimate from papers like Buchel are about 10% supercooling. And again, there's like at some point, the geometry becomes so curved in the IR that actually it sort of starts being unstable and populating small black holes. So just instabilities are hard to simulate numerically. So yeah, this is sort of qualitative, but still parametrically small supercooling. And there's recent work by Lisa and Rashmi Mishra, who's a postdoc at Harvard, which tries to model this behavior with sort of a goal otherwise is going away from the small back reaction limit of the kind I was describing earlier. So the whole sort of thing seemed to be that you have a small back reaction of the stabilizing geometry, so you have a light radion, and that does always give you a very strongly supercooled transition. But if you actually now start turning on in some controlled way large amounts of back reaction, you suddenly see that goes away, and you start actually seeing instabilities even in the RS effective field theory construction. So there's some work on that recently. So in fact, this sort of starts pointing us towards the fact that supercooling is not generic. And so I'm going to present two things to you now, not going into too many details. One is what kind of a model would it actually require in a 4D gauge theory to produce a confining transition that gives you large gravitational lucidity. So this is again not to model build to get something. This is to see what does it take to actually get something. This is trying to see what mechanisms do you need to actually produce an effect like RS. So and then I will present what the evidence for why there's no additional evidence. Already sort of this ADS-CFT evidence and the Klebanov-Strassler evidence sort of suggests that maybe confining transitions aren't typically supercooled. As soon as you get to a regime where the coupling starts running strongly, you get instabilities, and there's no reason to expect it to supercool an order 1 fraction below the critical temperature. But I'll present some direct lattice evidence why we think that in SUN Yang-Mills theory, supercooling should be small. And let me think about the time. So in the interest of time, I'm not going to give you, we can go into the details of this model, but I think probably in the interest of time, I'll gloss over them, but I'm happy to talk about them afterwards. But let me give you the kind of 4D gauge theory that looks like RS that might work. So the idea is to try and replicate RS just to see what it takes, and to then decide whether we think this signal that one of the target signals for the satellite we're going to send in space is a generic signal, or it's a very sort of narrow signal. It's not really something you'd expect for a strongly coupled theory to do. So the basic picture is this. So we're trying to replicate the idea of the spontaneous confinement that some scalar field, which was the radion in the RS case, actually triggers confinement. So what our basic picture is that we have a strongly coupled field theory near a fixed point, and there's a scalar field that it couples to that triggers its confinement transition and puts it away from its near fixed point. And so it's a very simple idea. Consider some SUN gauge theory maybe at large n, at large n C, and let's put it in the conformal window. We don't really know what the lower end of the conformal window is. The higher end of the conformal window can be perturbatively calculated, but it's believed there's some lower end of the conformal window, and there's close to the lower end of the conformal window, when the number of flavors hits this n-con, there's a strongly coupled conformal fixed point. But we don't know if it exists. In SQCD, we have much better handles on this thing, and we think at 3 halves NC, there's actually a strongly coupled fixed point. We're going to stay away from supersymmetry. We are interested in the non-supersymmetric phase transition. That's as the simplest, as the most generic possibility. And so we consider some theory that's living close to its conformal fixed point in the conformal window, and we add to this theory, to the Yang-Mills-Lagrangian, just a scalar field theory that there's some scalar field, it has some potential, doesn't really matter, and its job is that if it gets a web, it gives mass to the quarks in the theory. So essentially, this is the simple idea is this: you have some number of flavors and colors which are locked in such that we are close to a conformal fixed point. A scalar field gets a web and masses up the quarks. So then the theory notices, oh, the quarks are heavy, so I'm just a pure Yang-Mills theory. And I'm at strong coupling, so I'm going to confine rather quickly. So this scalar, if the scalar has a phase transition in its web from 0 to some value, the fermions get a mass, and right below the mass, you suddenly confine. You confine rather quickly because you were at strong coupling to start with. Okay, so the same in a given transition where the scalar field theory undergoes the transition, a bubble forms. Inside the bubble, the scalar field has a web. The bubble inside the bubble, you already have confinement already, and outside the bubble, it will be confined. So this is like a triggered confinement model where the scalar field sort of triggers the confinement as soon as it undergoes its phase transition. Okay, and this has sort of, at least this is like sort of a toy version of what really the RS phase transition somehow looks like. There's an external scalar field in that case, which is a light radion, and that triggers this spontaneous confinement. So anyway, so I'll spare you the details. The upshot, maybe I should, I'll really spare you the details. The upshot is actually it's not entirely easy to make these phase transitions happen together. These are strongly coupled theories, so you don't do detailed calculation, but you can do NDA, and you can't, for example, as we're discussing, you don't want to violate, that at one loop you choose couplings which at one loop are too big, are corrected to be much bigger than that. So if you choose everything to be at the NDA level, it turns out that it's hard to make everything work. You have to sort of introduce quite a bit of structure and choose parameters carefully, such that the scalar field transition happens at the same time as confinement. So you don't want something like the standard model where the Higgs transition happens, the electroweak transition happens, quarks get a mass, but eventually QC confines. Nothing to do with the quark mass in that case. But you don't want some separated transition. That's not what you would call a triggered confinement transition. You want something that happens right away. And so you want the scalar field transition and the values to be such that the fermions essentially the fermion mass is above the confinement temperature at a given temperature. And so again, you can make it happen. So if you're interested in making a confining gauge theory give gravitational waves, this is a parameter space, and I can explain it in more detail. But the idea is it's not generic, and it certainly requires a lot of construction. Even the initial setup was something constructed to reproduce what RS does. So it's not a generic attractor behavior of some strongly coupled gauge theory that you just get a large strongly coupled phase transition. Question.
In this case, we're not claiming that there's necessarily a light dilaton.
Here, there's no light dilaton. The trigger is just sort of some.
This thing will have to sort of strongly first order phase transition. There's never a flat direction.
There's never a flat direction, no. There's no light dilaton in this case, but we have put an external So in this RS model, the sort of light electron is a light field compared to the rest of these, and it acts as an extra trigger, right? In this case, we actually put in the trigger by hand. So we don't need light, we just need these two minima, and that does the job of the transition. So there's no spontaneous, but it's a triggered confinement where the scalar field calls the shot of what temperature would it confine. When the scalar field goes, then that then confine. Otherwise, it's sitting close to its component. So that feature is similar, but there's no spontaneous confinement. I don't know of an example of spontaneous confinement. But there's various. I mean, if you start doing the NDA, there's various structural limits where actually you want to generate the quartic radiatively through Coulomb environment potential and things like that to actually make this work. But it can be made to work without massive tuning, but requires a bunch of structure. So I think I would agree if I gave you the details, it's not generic. Okay, so I went through that fast because I wanted to get to just thinking about supercooling in SUN itself. And so the confinement transition in SUN, Yang-Mills theory is something of a holy grail, and it has been studied extensively, including on the lattice. And the lore is that the transition at large n, it goes like n squared, and so then you expect it to be a very loud first order of a transition, and so large n theory should give you tons of gravitational waves. So the lattice confirms that for n greater than 2, it's a first order transition. And at the critical temperature, you can calculate the tunneling action from these various quantities, the latent heat and the tension of the bubble wall in this particular case. And so you see that it is indeed true that the action scales like n squared. And this is just sort of the generic temperature dependence of the tunneling action. So this is what you'd expect, order n squared or epsilon squared. But actually, if you look at the numbers, there's a 10 to the minus 3 number that is unexplained. That comes out of the lattice fit.
The wall you would calculate.
Yeah, so indeed, the tension of the domain wall, it's exactly sort of the sigma cubed on the top here that is small. So the domain wall tension is smaller by sufficiently that actually this tension is this action is parametrically smaller than this pattern. And so this could just be a number. There's no small coefficient anymore. There's no free parameters. We've taken account of the n, and so we don't understand what this small number is coming from. Yeah. And so this small number, what we claim is telling us that actually the action is trying to get to 0, and it's going to get to 0 very quickly, very close to this temperature, in fact. And so this small number, in fact, directly translates. This is a lattice number that translates into an expectation for how quickly the active will actually go to 0, and there will be a classical instability in the confinement range. Okay. So that's the observation that just like in the ADS-CFT case, just like Levinov-Strassler, this is also telling us that the small number is also telling us actually that there's an instability close by to the critical temperature in the deconfined phase, and it's going to confine without any barrier very close to the critical temperature. And so for this, detail. Okay, so to really okay, so to make a mapping, we again use a toy example where we can actually compute the action as a function of temperature, and use that to calculate. So maybe I should say, again, for various reasons, most lattice studies there's a lot of lattice studies on this transition at the critical temperature, because that's conceptually and numerically easier. But there are studies which I will cite perhaps in a couple of slides, which look at the action as a function of temperature, but nobody's looked at so far what happens if you supercool by an order of a number, by a few percent. So most studies study either superheating and or they study things at very close to the critical temperature. And so there's this on the lattice, one could just ask, what is the supercooling? Just find the action for tunneling as a function of temperature instead of just at the critical temperature, and then you can see what that looks like. But we don't yet know what that looks like, and we're trying to get them to do that. So an example of what that functional dependence might look like, we can extract from a toy theory, just like using ADS-CFT or Clemens-Strassler. So here's the toy theory again. I'll skip all the details in the interest of time. Where we study the same problem in a supersymmetric version of the transition, where the transition itself is supersymmetric, and we try to find the action as a function of temperature. And what we want to find is just sort of a generic functional form of what the temperature dependence of the tunneling action is, and use the lattice data to match onto what we extract information from that coefficient, saying what does that functional form look like, say, in this toy example, and use the same functional form to actually learn something about those confinement terms. Okay, and perhaps once I actually have equations on the model. So a toy model is we put n equals 1 super Yang mills on R3 cross S1, as you would do for a thermal transition in super Yang mills. If you just put it on a thermal circle, then it's not very different from actually the Yang mills theory, because temperature already breaks supersymmetry. If you want to actually keep the calculability of that supersymmetry buys you, you actually put fermions to have a periodic boundary condition. So there's a supersymmetry, and just as said before, this partition function now is actually just a topological invariant, so there's actually no transition. But as was studied by these people more than a decade ago now, this actually, if you actually add a mass for the gauge, so you add a calculable small supersymmetry breaking, there's actually a transition between the center symmetry breaking and the center symmetry preserving phases, which they argue is continuously connected to actually the thermal Yang-Mills relationship. So this, at least in the small, whether or not you want to connect it to the thermal Yang-Mills transition is a separate question, but it provides us with a toy model for small m. The transition actually happens for small l, which is high temperature. So actually at weak coupling. So there's the supersymmetry buys us this extra handle where the center symmetry breaking transition, which is analog of the confinement transition, happens calculably at weak coupling. Okay, so this is the toy model we'll use to actually just try to figure out what does that look like as a function of temperature, what does action look like as a function of temperature, and then try to extract information. The way the calculation progresses, again, skipping details, is to look at the order parameter, which in this case is the Polyakov loop, and it's in this. At recoupling, you can just calculate the potential, and you can just, for example, for SUT, the potential looks like this, where there are two scalar fields. This is the deconfined transition. This is the deconfining minimum. This is the confining minimum, and you can study it as a function of temperature, and you can just calculate the turning action as for a scalar field. You would for calculating it for any given temperature. Okay. Yeah, happy to say more if there's questions. But here's what it looks like. You can calculate the bounds action as a function of temperature, or epsilon in this case. And this is typically what it looks like. There's some, and this is plotted for different ends. So we went from N3 to 15 or whatever. The 0 is where the critical temperature is. So this is what the lattice sort of would tell us, what is the bounds action at the critical temperature. And we see what it does as a function of supercooling. So if you go towards the right, you're supercooling, you're going below TC. And as you go to the left, you're superheating, you're going above TC. And indeed, you see that there's no small slopes in the temperature dependence of the action. So the fact that the action is small here means it's going to hit 0 rather quickly. So that's sort of just a very generic statement that there are no small numbers in the action's dependence on temperature. So the fact that lattice tells us it's small, and TC tells us actually it's likely going to hit 0 close by, and so supercooling is going to be small. We can actually extract a generic form for the action from this, from this, which looks like essentially epsilon minus epsilon superheating times epsilon minus epsilon supercooling over epsilon squared. which describes this data really well. And so if you just use this functional form to fit the lattice data, we can translate these results from this toy supersymmetry example to the actual Yang-Mills results. And what that tells you is that the product of superheating and supercooling is order 10 to the minus 3. And supercooling and superheating is typically expected to be larger than supercooling. Also because sort of, if you imagine a gauge theory running at high temperatures, the coupling is small, it's running and reaching TC. And then as the coupling becomes larger, all dynamical effects become faster. So the dynamical scales shrink as you go more and more to the IR. But in any case, that's what you see here in this toy example. And so even if you assume supercooling and superheating are similar in strength, you would get an estimate for supercooling, which is about 8%. So these are all, this translation is from a toy model, it's a qualitative estimate, but this small number, we argue, is correlated with the smallness of supercooling and superheating in gauge theories. The superheating estimates for various, the superheating estimates for SUN Yang-Mills, which are order 10%. So roughly around this ballpark. And we expect the supercooling to be also something around that, something like 5%, 10%. It's intriguing that this 1 over d squared, 1 over 16 that we got from ADS-CFT seems to also be sort of the rough estimate for what's going on for just pure Yang-Mills supercooling. So just to summarize, from the phenomenological point of view, gravitational waves signals rely on strong supercooling to the confining phase transition. And the typical model, one generic target for those is a confining phase transition. And in phenomenology, we often study that in the context of the RS model. But it relies on a trigger to break conformal invariance and do the confining transition, which seems rather non-generic. And certainly we don't see, by no supercooling, I mean no appreciable supercooling above a few percent in ADS-CFT or Klebanov-Strassler constructions. And we have a quote-unquote prediction that the supercooling in SUN, Yang-Mills theory, would be a few percent. And this is something that is in principle testable on the lattice, so it would be really interesting to see if that's what they found. Thank you.
How did they compute? I guess you're saying they compute basically the bounce action for superheating on the lattice, but how do you do that? Do you
I'm not an expert on I'm not an expert, but what they calculate is they choose some order parameter. They could be polynomials, but they're arguing now that it's not necessarily the best one. And then just calculate the distribution of the order parameter in their Monte Carlo. And then they find a distribution which is sort of, if it's like a metastable thing, that sort of would be a bimodal distribution.
Yeah.
And the minimum of that distribution, so yeah, if you like imagine something like a Polyakov loop distribution, it looks something like this. And the minimum of the distribution is supposed to be the sort of the separatrix or the critical boundary between the two phases. And so they calculate that, and they calculate that free energy, and from that they estimate the bubble wall tension. So they say this phase is somewhere, this minimum is where the two phases are coexisting. So there's some amount of bubbles in the distribution, and so from that they extract the bubble wall tension. Again, I might be not doing it justice, but that's what I understand. So and it's sort of, this is exponentially smaller typically for these things than these peaks. So they actually have to do some clever things so most of the papers I try to read are about how cleverly they reweight and so on to make sure that they actually sample this very small.
Yeah.
Yeah. And they claim that, well, they do say that superheating is somewhat slightly easier than supercooling for technical reasons. But again, I'm not sure exactly what.
I have like a super dumb question. Like, so the conclusion was this prefactor, kind of dimension of prefactor was small, right? And SUN, and therefore, a few percent of the expected answer, but the expected answer still scales like n squared. So what is n here? If n is big, is
Oh yeah, so that so this exactly good. So it's not, we're not meant, so the statement is it's epsilon, it's on 10 to the minus 3 times n squared. Right. So you said, like, well, big book, I take n to be 100.
Right.
So isn't that okay?
Yeah.
So this action will be large, but that epsilon is not saying that it's 10 to the minus 3 n squared as a function of temperature. It's still going to only supercool a few percent. So it's going to go that everything is going to go, because the slopes are order n or n squared, whatever. So slopes are order 1 in n squared units.
Yeah.
And the number is epsilon in n squared units. It's going to hit 0 quickly.
within order 1.
Within order epsilon.
Within order epsilon.
So the supercooling is going to be small, so it's going to hit 0 and it's going to be instability. So that's what this is n equals 15 and it's still like under a few percent here. See, so the action is not, action being small in number is not necessarily the point. It's the fact that it's always there's no smallness in the slope, and so it's quickly going to go to 0. Yeah, so if you focus on the critical temperature, you'd say, oh, there's still a barrier, big, I can make it as big as I want, there's still a loud phase transition. But you don't care about that when you actually do dynamically do the tunneling. You wait a little bit, and the barrier sort of disappears, and you just go. So the actual transition doesn't happen at the critical temperature. So that's this dynamical metastable thing is harder to model than just thinking about the critical equilibrium. So that's sort of that's why it's not a natural thing to ask when you think formally about the question or thinking on the lattice, unless you really look for that supercooling or superheating. When you're really looking for a dynamic process.
But is there some criterion that you can formulate, say, the equilibrium effective potential or something?
So say again, sorry, what?
I'm a little bit confused about the examples that have the supercooling versus the ones that don't. What feature would warrant your modeling? All of them are described as some kind of effective model of the transition, landmark instrument model or something.
Well, so in the case, like if you have just a scalar field theory,
Yeah.
and you choose your effective, you can make the transition whatever you want. You can make it as first order as you want. The question is, if you take a generic strongly
For
coupled.
example, your point is that being very first order is what we're doing.
But first order and supercool, whatever you want. Just scalar field theory, you just have complete control over your Lagrangian, and you can just calculate, and it's weakly coupled, and so there's typically also in those cases, by the way, you have to really have a loud gravitational wave signals. You have to be on the boundary of almost not completing, because if you made the barrier slightly higher, you would just the tunneling rate would be so small that it would not complete in the Hubble time. You'd just be tunneling inflating, you create more. And so you always have to live with the boundary. But in scalar field theory, there's no, you can do that. You can do whatever you want. The question is that, well, if you have new scalar fields and they do whatever you want at TV scale, that could produce gravitational waves. It would be really interesting if there was a strongly coupled phase transition, like kind of like the QCD. QCD doesn't quite work, but something like slightly larger n that generically just is loud. And we thought it was loud because it's n squared. And so we said, look, forget about all these scalar fields that you have to invent and everything. If there's compositeness and larger, and you just get loud phase transition at the weak scale. So it's just, you should just go look for them, and that's like a generic signal. And that hope is dashed because even if the action at the critical temperature is large, it actually doesn't supercool enough to actually give you gravitational waves. So this is a generic, so because there's not too many handles, you give me a gauge theory, it does what it does in the IR. I can't tune the potential and effective potential for various things. I don't get to choose what an SUN gauge theory does. So
imagine you fantasize that by somehow tuning, you add some fermion or something, you somehow tune to the boundary of the control where you have the periodic noise, but you have something that runs very slowly. Get something that has a nearly mass silicon. That's actually conceivable. We don't know that for sure, but what do you think? Is that enough to guarantee the supercool? Just having a light dilaton? Or do you need more than that?
I think it's probably the light dilaton is some scalar field theory, which is weakly coupled. A weakly coupled
It's not just weak. Most of.
Yeah. So the smallness of its mass or whatever it would be translates into smallness of the shift symmetry translates into being weakly coupled roughly.
Yeah.
And so weak coupling is the action R1 over lambda, right? E to the minus 8 pi squared over lambda or whatever. So small weak coupling scalar field driving a transition will give you will give you a strong phase transition. That's a first order phase transition suppressed and so on. So if you have something, and again, you could just take a weakly coupled scalar field theory with small lambda.
That scenario is not first order.
Well, so it depends on the potential. Yeah, you have to get.
It's really more second order. I mean, if you have this scenario with an emergent massless dilaton, it's really kind of a second order. It's a continuous transition.
But the emerges as a dilaton. But if the dilaton just for whatever dynamical reasons had its own potential, so once you're in the effective field theory of the dilaton, and the dilaton itself had some barrier potential like this, and it was
But I don't think that's not really a dilaton. Then you don't have the situation like in RS because this doesn't have control. Not even spontaneous before.
No, but so again, this is small. So this is all the whole potential is small because of this goal otherwise. But this is what in the RS case, this is what the potential. Well, the potential for the RS case looks like this. So there's a V pi, and typically looks like this. And this side is gravitational. So this is like saying that the radion at 0 is like saying the IR brane is off to infinity. And the potential that the stabilization mechanism generates looks something like this. And so what people calculate is this tunneling action. And that's what the typical calculation was. So having the radion is not enough. You can just have a situation where it just is like this and there's no barrier or whatever. But if you have a scalar field which is weakly coupled, then it's not hard to imagine there's a barrier that is.
Fine-tuned case where the radion is exactly flat. There you don't care.
In the fine-tuned case, there's no transition because as soon as you turn on a temperature, the brain disappears. So there's no transition. Yeah, it's always deconfined at every temperature, any temperature. So finite temperature potential. There's a finite temperature T squared potential for the radion, so it just goes off to 0.
More questions for Prateek? All right, let's thank him again.